So, for 7.6, the lesson assumes that you know something that you might not necessarily know, so I split it into two sections. So we have 7.6a today, which deals with right triangles, okay? So we should know that a right triangle is called a right triangle because it has what kind of angle in it? A right angle. So there are two vocabulary words that you need to know, and you probably already know this, but if you have it written down somewhere, at least you can reference. A right triangle has two legs. The legs are the two sides of the right triangle that form the right angle. So in this one, it would be this side and this side. So the leg are always the two sides that form the right angle, even if the triangle does not look exactly like this. Even if it's rotated, the legs are still the sides that form the right angle, okay? Right triangles have a special side called a hypotenuse. The hypotenuse is the side of a right triangle that is opposite of the right angle. So it's the diagonal side, okay? The hypotenuse is also the longest side out of all three sides on the triangle, okay? So, 7.6a, we're talking about the Pythagorean theorem. The Pythagorean theorem is called the Pythagorean theorem because it was named after the mathematician who derived it from ancient Greece. His name was Pythagoras, okay? So, his name was Pythagoras, so it's called the Pythagorean theorem. Okay, so the Pythagorean theorem only applies to right triangles. So I drew a nice big right triangle. We can assume that this is a right triangle. Why? Because it has a little box, which means that it is what? 90 degrees. So let's write that. Right angle, which means it is 90 degrees. That's what the box means. Okay? Now, according to our two definitions, we have two legs and a hypotenuse. Yes. One leg is right here, so we're going to label it for right now. And the other leg is along the bottom. And the hypotenuse is that diagonal. Okay? Hypotenuse. One thing I want to point out to you guys, if we labeled this triangle, label A, or triangle ABC, ACB and ABC still form the same triangle, okay? But I just want to point out to you how we name these. When we are naming triangles, we call the side that's opposite of the vertex that side. So, for example, this leg would be called leg A because it's opposite of point A. Does that make sense? So we would call it lowercase a. So we use lower cases to name the sides of triangles, and it's opposite of the angle it's diagonal from. So what would this leg be called? B, lowercase b.
The hypotenuse C.
And the hypotenuse would be called C.
How would you write a lowercase c?
Just smaller than the big one. Okay? What does this have to do with anything? This is where the Pythagorean theorem comes from. So, I'm actually going to give you guys a choice. Do you want me to give you the Pythagorean theorem and then we will prove it, or do you want to prove it and then I'll give you the theorem? Get it first and then prove it? Okay. So here's what we are going to do. I wrote it nice and big because guess what? It's super important. Here, let me see if I can get it with the triangle in there.
More important than my life.
Okay, so it's super important. I wrote it really big, and I'm going to put the whole thing in a box. And then I just wrote a note to myself. The Pythagorean theorem only applies to right triangles. Okay, if it's not a right triangle, you cannot use the Pythagorean theorem. Does anybody already know what it is? Matt Dolia.
The formula?
The formula.
A squared plus B squared equals C squared.
A squared plus B squared equals C squared.
What? I don't like it. This guy's super important.
Okay. A squared plus B squared equals C squared.
I get it.
Meaning the sides. So that's why we labeled all of the sides too. So if I take side A and square it, and then add it to side B squared, that will give me side C squared.
So we're actually gonna look, so that's what our homework is gonna be about?
Mm-hmm. Lots of triangles, and we're going to find lots of missing sides.
Yay.
Mm-hmm.
That's the times you had.
Let's prove why this works, okay? So you guys are all going to get, in a second, a little slip of paper that has 3 squares on it. A small one, a medium one, and a big one, okay? When I tell you to, you guys are going to go get your pencil boxes to share among your groups. And I just want you to cut out all 3 of those squares. And then that's all that we are doing with the supplies. So as soon as everybody in your group is done cutting out and you have 3 squares, you are done. And you can put them away. Got it?
Got it.
Okay. So please lay out your 3 squares for me. And we're going to do first, what we're going to do is we're going to prove the Pythagorean theorem using this specific example. And then we are going to generalize it, okay? So we will generalize it, so I just want to make sure that you guys are not getting too caught up on the actual number of squares in here. So will you please look at the smallest square? Turn to your partner and figure out together what the area of this smallest square is. Haley, what's the area? 9, good. Okay, look at the medium square. What is the area of the medium square? Okay, I heard 2 different things. 16. Okay, what is the area of the larger square? 25. Okay, so now I want you guys to tell me, does everybody agree that the small square, 9, plus the medium square, 16, equals the large square, 25? 9 plus 16 gives us, okay, doesn't that sound familiar? Right? Where did the squares come from? Finding the area, because this one has a side of 3, and 3 times 3 gives us 9, so this is 3 squared, right? 4 plus times 4 gives me 16, so this one is 4 squared equals 5 squared, right? Okay, so what the heck does this have to do with triangles? Triangles make up squares. Can we make a triangle out of these squares?
Yeah.
See if you can figure that out. If I make,
There's no logic behind it. There really isn't.
and then here's your hypotenuse.
Oh my gosh.
Oh, I got it.
Such a genius.
Do you guys see the triangle?
Brains everywhere.
What is this supposed to be?
Okay, how does this tie to what we just did? What's the length of this side? 3. What's the length of this side? 4. And what's the length of the hypotenuse? 5. Okay. So then the area of the leg squared, so the leg squared, A squared, plus the area of the second one, B squared, equals C squared. And we can prove it because they form a triangle. Okay? So here's what I want you guys to do. Do not write on any of this, but I'm going to give you 1 minute. Glue these in like this onto your left page, and then we're going to label it generalizing this concept. Okay? Okay, so how does this generalize? First of all, we know that the right angle is right here, correct? Okay, so here's what I want to do. I understand that this square has an area of 9. However, when we are proving something, we always want to use generalization. So, what if I didn't know that the area of this was 9, and all I knew was that the side had length A? So I'm going to label all the side lengths A. What would be the area of this square?
You would not be able to know because it's all A.
How could I represent it using just the A's?
A to the 4.
A times A, which is A squared. Because you find the area of a square by multiplying length times width, right? Okay. What if I also did not know that this one had an area of 16, but all I knew was that the side lengths were B. What would be the area of the square?
B not
B squared.
We're not even saying square.
And then the same thing, what do you think I'm going to tell you the side length of the big one is? C. So if all the sides, because it is a square, are length C, what would be the area of the big square? C squared. Okay, but we do know that all of this area plus all of this area gave us all of that. So what can we say? A squared plus B squared is going to equal C squared. And I formed a right triangle that has legs A and B and a hypotenuse C, which is exactly what we had with the Pythagorean theorem. Does this make sense?
Yes.
Why it works?
Yes.
Okay. There are actually like hundreds and hundreds of proofs of the Pythagorean theorem. This is probably the most famous. There's a second one that's also very, very famous, but I like this one. No. That's why it's a theorem and not a postulate. So a postulate is something that we just take as fact. A theorem is something that has actually been proven to be true. Okay? So how does this apply to problems? I'm going to do 2 examples with you.
No, that doesn't work.
Okay? So here's 2 examples. Example 1, I give you a triangle with side lengths 6 and 8, and we're going to find the missing side. Okay, guys. I have 6 and 8, and they're on the sides that form the right angle. So both of these are what? Are they legs or hypotenuse?
Legs.
They're both legs. So I'm missing the hypotenuse. What letter do we want to give that? C. Could I call it X? Yes. It really doesn't matter. Okay, so the Pythagorean theorem says A squared plus B squared equals C squared. So here's the first step. You plug in what you know. 6 squared plus 8 squared equals C squared. The reason I want you to show all of these steps is because sometimes we will be solving for one of the legs instead. We want to do it all algebraically. You guys should all know what 6 squared is. What is it? 36 plus 64 equals C squared. What does 36 plus 64 come out to? So we get 100 equals C squared. Did I solve for the length of the side?
No.
No, because I have C squared, but I'm looking for C. So what's the opposite of squaring something? Square rooting it. So square root both sides, because whatever you do to one side, you have to do to the other. So the square root of C squared is just C, and what's the square root of 100? 10. So your hypotenuse has length 10. So for example 2, I actually give you a leg and what? The hypotenuse. So I'm missing this leg. Do you guys want to call it A or B?
B. I prefer B.
It doesn't really matter. Let's call it A.
Ah.
If you want to call it B, call it B.
I call it B.
Okay, so let's plug in what we know. I don't know what A is, so I'm going to leave it as A squared. Plus B squared, which is 4, equals
44 squared.
C squared, which is 24 squared. Okay.
I can't do that in my head.
I don't know what A squared is, so I leave it as A squared plus 16 equals 24, 576. So then we subtract 16, so we get A squared equals 560. And then what do we do? Square root it. Okay, I'm going to show you 2 ways to write your answer. Okay, the square root of 560. We cannot leave our answer like that. What's your first instinct?
Square root it.
Square root it using what?
Calculator.
Calculator. Okay, so let's do that first. Okay, it comes out to what? 23.68? Okay, we'll just go with that. Okay, so you can do that. If we're going to do that, I mean, you can put equal. The approximate doesn't super matter to me. Or we can also use what is called radical notation. Okay, meaning we're going to look to see if there are any perfect squares inside of 560. So, 560, I'm gonna just do a little factor tree off to the side. Does anybody know what perfect squares go into 560?
23. 23.
23's not even up there.
23 squared.
So we know it splits up as 56 and 10, and 56 is 7 and 8, and 8 is 4 and 2. Okay, did anybody find a perfect square?
4.
4. Okay, so here's what we do. Oh wait, and then 10 is 5 and 2. So there's another perfect square, 2 and 2, which is 4. So we pull out 16. So we pull out a 4. Okay, because guys, here's what I'm doing, and we'll go over this a little bit more in detail, but does everybody agree that 2 times 2 is 4?
Yeah.
And then we have a 4 here as well, right?
Yeah.
So 4 times 4 is?
16.
What's the square root of 16?
4.
4. So we can pull that 4 out of the square root. Hold on. What could we not pull out of the square root? 7. Oh wait, no, 8 was 4 and 2, so we did that. 7 and 5. So that stays inside the square root as 35, and it comes out to 4 root 35. When you put that in the calculator, it also comes out to 23.68. Here's what I want you to do. On your homework, you are more than welcome to use a calculator. Try to also keep it in radical notation, okay? Just try.